This video is a review of energy for AP Physics 1. When we started off talking about energy, we first talked about a topic called work, which we defined by saying that if a force F is exerted on an object and that force causes the object to move through a distance d, then work is being done on that object. And conversely, if a force doesn't cause an object to move through a certain distance, then no work is being done. In the picture here I have a force F that's going through a right, and it causes it to move through a distance d. And so their work is being done, and the amount of work that's done by that force is equal to that force times the distance over which it was exerted. And when the force is measured in newtons and the distance is measured in meters, the work can be calculated, and that work would be measured in joules. And we say that the work done on that object causes its energy to change. And maybe that makes sense because if I exert a force on an object to lift it up, I can change its height. And if I use a force to move an object to the right and give it some speed, then that work is causing the object to speed up. And so work can increase or decrease the energy of an object. In talking about work, we learned that the W equals FD equation is not the full story. The actual equation, in order to represent work properly, needed to be FD cosine theta. And that's because for work, only the forces that are aligned with the displacement vector do work. So for example, in the top picture that I have here, the box is moving to the right with a speed v. Maybe I'm pulling up on the box at an angle, so maybe I'm tugging on the box with a rope that's attached to the center of the box, causing a force F to be exerted on the box like that at that angle. Only the force that is parallel to the direction of the velocity or the direction of the displacement does any work. And you can see that if you made a force triangle there, that would be F cosine theta, and maybe that makes some sense or provides some reasoning for why the equation is FD cosine theta, because F cosine theta represents F parallel, the component of the force that's parallel to the displacement. And so for any angle that's between 0 and 90 degrees, the work done will be positive, and the reason why the work is defined as being positive is because in those cases where the angle of the force is between 0 and 90 degrees, that would cause the object's energy to increase, and so positive work increases the energy of the object. In the second case, you can see that the component of the force that would point along the direction of the velocity would actually be pointing in the opposite direction. The angle is still defined as the angle between the direction of the velocity or displacement and the force, and so here the angle is actually between 90 and 180 degrees. And if you plug an angle bigger than 90 into a cosine equation, you'll find that the resulting answer is negative. And for that reason, the work done by a force that is directed 90 or more degrees, well, more than 90 degrees away from the displacement vector, causes the work to be negative. And we say that if work is negative, energy is being removed from a system. So if you imagine the box moving to the right and me pulling on a rope directed as it is with the force in the second case here, then that would actually cause the object to slow down. A more practical application of negative work would be the case where the force is directed 180 degrees away from the direction of the motion. That would be the case of friction, where the object maybe is moving to the right, the friction is directed to the left, and so those two vectors would be separated by 180 degrees, and the work done by that frictional force would be negative. And so these last 2 points here are pretty important. If theta equals 0, the cosine of 0 is equal to 1, and so the equation up above turns into F times d times 1, or just F times d. And if theta equals 180 degrees, like in the case of friction, the work done is F times d times negative 1, because the cosine of 180 is negative 1, and so the work done is minus F times d a negative amount of work. And as I've said, if the work is positive, then that means the energy of the object is increasing. And if the work is negative, the energy of the object or the system is decreasing. If the energy of an object can increase or decrease due to the amount of work on it, it makes sense that we need to talk about the different forms of energy that an object can have. And so quickly I'd like to review these forms of energy by saying kinetic energy is the energy of an object due to its motion. So the faster an object is moving, the more kinetic energy it has. But it's not a linear relationship between the speed and the kinetic energy. Actually, the kinetic energy is proportional to v squared, which means that if the speed of an object doubles, then the kinetic energy will be 4 times greater. However, the kinetic energy is still proportional to the mass, so if the mass increases and the speed stays the same, for example, then the kinetic energy will still be increasing. So a regular sized car and a big truck that are both driving at 30 miles per hour, the truck has more kinetic energy because it has more mass. However, it's possible to give the car more kinetic energy than the truck by just simply having it move at a speed that would be greater enough than the mass of the truck in order to cancel out the effect that its mass has. For gravitational potential energy, that is the energy of an object due to its position in a gravitational field. And so it depends on the mass and it depends on the strength of the gravitational field, but most importantly the relationship that really matters is that relationship to the height. So the further I raise up an object in a gravitational field, the more energy is associated with that position, because if I let the object go, it can fall back down along the direction of the gravitational field. And so for that reason, we say as the height increases, the gravitational potential energy increases. A couple of important points with that: an object alone cannot have gravitational potential energy, and that's because we need the gravitational field from another object in order to pull on it. And so we can say that a book has gravitational potential energy as part of the book-Earth system. So the further up that I raise the book, the more potential energy it has because it is part of the system with the Earth. So the object alone doesn't have the gravitational potential energy, only the book-Earth system. And also we talked about something called elastic potential energy, which is the energy of an object due to it being stretched or compressed. So things like rubber bands or springs are able to be stretched or compressed, and we know that those objects can store energy because when we let go of them, they might shoot back and forth, right? If you extend a rubber band and then let it go, it can fly across the room, and so that kinetic energy had to come from somewhere. There is some elastic potential energy, US, stored in that object. And that elastic potential energy is proportional to the amount of stretching or compressing squared. And so if I stretch or compress an object, I get to store some elastic potential energy. And the K in this equation represents the spring constant of that. So for a rubber band, maybe it would be more difficult to define the spring constant, but we've definitely seen cases where we've used springs that obey Hooke's law, that when you stretch or compress them, they have a well-defined spring constant. All of these forms of energy are measured in joules, and they are all scalars, which means that they don't have a particular direction associated with them, just a magnitude and a unit. Sometimes when we talk about energy, we use the phrase mechanical energy. Mechanical energy is the sum of the kinetic and potential energies of an object, and that's where we spend most of our time in AP Physics 1. We talk about kinetic energy, and then we talk about a couple different types of potential energy. So mechanical energy is sometimes represented as just a capital letter E for the total energy of a system. And that could be due to it having some kinetic energy, potential energy, one of the either or both. And so make sure that when you see U, you know that it could not only be gravitational but also elastic potential energy. And then sometimes, in rare cases, we've defined a gravitational potential energy where even in cases where the gravitational acceleration isn't constant over large distances, we can have an expression for the gravitational potential energy. And one of the things is, in our previous equation for gravitational potential energy, we see that UG is equal to mgh. And so near the surface of the Earth, it makes sense to use that equation because we know that G is equal to 9.8 meters per second squared. But as I start to move further and further away from the Earth over large distances, the acceleration due to gravity is not constant, and so it would be nice to define a potential energy associated with any position independent of that value of G. And we get the equation below, which looks a little bit like Newton's universal law of gravitation, but you'll notice that it's not a 1 over r squared relationship, it's 1 over r. The equation is also defined to be negative, and that's because this equation is defined in the following way. When an object is an infinite distance away from another object, the potential energy is defined as being 0. And as the object moves any closer than an infinite distance away, the potential energy becomes more and more negative. As two objects get closer together, if the potential energy is becoming more negative, that means the value is decreasing. And if the potential energy is decreasing, then the kinetic energy is increasing. And that makes sense. As two objects get closer to each other, the potential energy decreases and the kinetic energy increases. And the reverse of that is if r increases, so if the separation between two objects increases, then if you look at the equation, r is in the denominator, which would mean that the fraction is becoming smaller. But if it's negative, that means that the value of the gravitational potential energy is becoming less negative. And so if something is becoming less negative, the value of that is actually increasing. So as two objects get further apart, for example, as a planet orbits the sun, as the planet gets further away from the sun in its orbit, then the value of the gravitational potential energy is increasing. And that is in correspondence with a decrease in the kinetic energy, right? So as a planet goes around the sun, if it gets further away, the potential energy increases, it becomes less negative, and the kinetic energy decreases. And as the planet gets closer to the sun, the gravitational potential energy will decrease, it will become more negative, and the kinetic energy will increase. A couple things that I think are important to point out is that kinetic energy can only be positive, and that's because the mass is positive and the speed must be positive, or even if you treat v as the velocity is squared, and so for that reason the kinetic energy has to be positive. Gravitational potential energy can be positive, negative, or 0 because the location of h equals 0, and this is an important point, right? The location of h equals 0 is your free choice. So maybe we're working a problem where a ball is at the top of a ramp and it rolls down the ramp and then falls onto the ground. Well, if the ball eventually makes its way to the ground, then that is the lowest position that the ball will ever have, and for that reason maybe we define h to be equal to 0 at the ground. And then when it's at the bottom of the ramp at a height h1, or at the top of the ramp at a height h2, it will always have positive amounts of gravitational potential energy, and that makes some sense. But we could have defined h to be equal to 0 at the bottom of the ramp here. So if we define h is equal to 0 there, then when it gets to the ground it would have some negative amount of gravitational potential energy, and that's totally fine. And if you plug in that negative amount of gravitational potential energy into your equations, it will not be a problem. And we are also allowed to do that with, our, conservation of energy equations, in which case we are using our other form of gravitational potential energy, right? Minus g m1 m2 over r. That's already negative. And so we shouldn't be afraid to plug in negative amounts of potential energy into our energy equations, although typically we tend to avoid that by making some good choices with where we set h equal to 0. And lastly, elastic potential energy can also only be positive because the spring constant is inherently a positive quantity, and whether something is being stretched in the positive or negative direction, it doesn't matter because it's squared in this equation. And now I'd like to finally talk a little bit about the conservation of energy. And in particular, most of the problems we do are just conservation of mechanical energy equations. Okay, situations in which the mechanical energy of an object is conserved. So the sum of the kinetic and potential energies of an object are being conserved. And one way to write that down is to say that delta E, the change in energy, is equal to 0. Or we could just say that the initial energy is equal to the final energy. And when we say the energy of a system is conserved, and we do need to say the energy of a system, what we're saying is the energy of an isolated system is conserved as long as no external non-conservative forces act on that system. And so there's quite a few words in there. First, I'd like to point out the word isolated. What I mean by isolated is that I have to have a really well-defined system. If the system is a ball rolling down a ramp, I'm probably talking about the ball ramp earth system. And so defining the system for conservation of energy problems is pretty important. Maybe you remember that a non-conservative force is a force like friction that's path dependent. So friction, depending on whether I take one path or another, can do different amounts of work on an object. So let's say I'm pushing a box from one side of the room to the other. If I go the quickest route from point A to point B, then that's the smallest path and there will be the least amount of work done by friction. But if I decide to go left and then right and then go around in a circle and then go to point B, then the path was longer. And because friction is a force that depends on the path, right, the longer the path, the more friction, then it is capable of doing work on the object as I move from point A to point B. And if work is being done on a system or an object as it's being moved, then that means the energy of the object could change, in which case the energy wouldn't be conserved. However, if the only forces that act on a system are conservative forces like gravity, then the energy can be conserved. So for example, if I lift up a ball and I drop the ball, gravity pulls the ball down, and we have a conversion of potential energy into kinetic energy. As long as gravity is the only force acting on the object, then because gravity is a conservative force, we can apply the conservation of mechanical energy. And basically what that looks like is we write EI equals EF. The initial energy is equal to the final energy. And sometimes initially an object might have kinetic and potential energy, and sometimes it might have kinetic and potential energy in the final case. But more often than not, what we find is that typically an object will start off with one of these types of energy, maybe potential energy, and will end up with the other type of energy, maybe kinetic energy. And so for that reason, a lot of times we end up crossing off those terms and saying things like the initial gravitational potential energy, mgh, is equal to the final kinetic energy, 1/2 mv squared. And so those are cases where non-conservative forces aren't doing any work on the system. But if non-conservative forces are doing work on the system, and those forces are changing the energy of the objects in a system, then we say that that change in energy is equal to the work being done on the system. And we call this the work-energy theorem. Right? There's a relationship between the work done on an object and the change in energy of the objects in that system. And sometimes the change in energy might correspond to an increase or decrease in kinetic energy, and sometimes it might correspond to an increase or decrease in potential energy. So the second term should say delta U. Right? So the potential energy or kinetic energy could go up or down if there's work being done on the system, because that work could be positive or negative, and so the energies could be going up or down. In cases where the change in energy is equal to 0, where the mechanical energy is conserved, we could write a similar equation which looks something like this. We could write that delta K plus delta U equals 0. And in this case, since no work is being done on the system, then if the kinetic energy increases, then the potential energy would have to decrease. But that's not necessarily true if work is being done on the system. So we've talked a little bit about work and a little bit about energy, and the last topic in this unit that we talked about was power. And maybe you will remember that power is like the rate at which energy is being used, or the rate at which energy is being dissipated, or the rate at which work is being done. And since energy is measured in joules and work is measured in joules, power is always joules per second. And a joule per second is a watt. And so power is measured in units of watts. And maybe you remember running up a staircase, in which case we were plugging in an amount of change in energy that's equal to mg delta H into this power equation in order to calculate how much power we generated in going from the bottom of the staircase to the top of the staircase. We have a certain mass, we know what g is, and there's a certain height of the staircase, and in running up that staircase in a certain amount of time, you have generated some power, you've used up some energy. You're doing work to get to the top of the staircase. And the faster you do that, so in a smaller amount of time, the higher your power will be. So a few other important points. Kinematic equations can only be used when the acceleration is constant. And so if you see a problem where the acceleration is constant, like maybe for a projectile, it makes sense to use kinematic equations. But one of the most valuable things about energy equations is because they can be used even when the acceleration is not constant. And so I can use energy when the acceleration is constant, but even when it's not constant, like on a roller coaster where the magnitude of the acceleration changes as the angle of the ramp increases or decreases or goes around a loop, the acceleration is not constant, but we can still use energy equations. Also, I'd like to say that when I'm dealing with collisions or talking about where the energy is going in a system, then it's important to know about the kinetic energy and the potential energy, but it's also important to recognize other forms of energy. So if energy in a system is conserved, then that means we typically talk about a loss of kinetic energy and a gain in potential energy, but sometimes in a system energy could go not into kinetic energy, not into potential energy, but into other forms of energy, like maybe sound or heat or the deformation of an object. When two objects collide, like two cars for example, the fenders bend, and that bending, that deformation is corresponding to the energy loss of those objects. When tires squeal on a road, they generate heat between the tire and the road, and that's some of the energy being lost. And when two objects smack into one another, they generate sound, and that sound is the vibration of air molecules, right? And that energy has to come from somewhere. So make sure that you know about different types of energy that could correspond to some of the energy loss in a system. The last thing I'd like to do is to just talk a little bit about an example problem and what types of energy the object has and how we might implement conservation of energy in order to learn something about this problem. So for example, maybe we have a block here that's on a ramp, and it falls down the ramp, gets to a level section of track, and then collides with a spring. In general, I hope you know that at position 1 is associated with some gravitational potential energy that's due to the height. And sometimes that height is labeled quite clearly for us, but sometimes it's not. I've seen cases where the angle of the ramp is given and the length of this ramp is given, in which case you would need to write an equation. You would need to express the height of the ramp in terms of L and theta in order to write the equation for the gravitational potential energy at the top of the ramp. I hope you also know that when the object gets to the bottom of the ramp, that position 2 is associated with some kinetic energy, 1/2 mv squared. And then at position 3, the object maybe now is starting to compress the spring, and so there would be some energy stored in that spring, 1/2 kx squared. Now, if I look at any of the in-between positions here, so if I looked at this position here, where the blue star is, the object is kind of halfway up the ramp, and so it's going to have some gravitational potential energy there, but it's also going to have some speed because now it's on its way down the ramp. Similarly, if I were talking about a position right before position 3, so maybe the block is still moving to the right with a speed v, but it's also colliding with the spring. And so maybe in that position it's compressed the spring a little bit, but it's also moving. So at that position, not only would there be some kinetic energy, but also simultaneously some of the compression from the spring will give it some elastic potential energy. Also, if there was some friction on this ramp, right, as the block was moving down the ramp, there would be a frictional force that opposes the motion of this object. And for that reason, some of the energy of the object that was initially gravitational potential energy would not get converted into kinetic energy. And so typically we tend to think of all of this gravitational potential energy being converted into kinetic energy without any loss. But if there's friction, and if that frictional force is exerted over a distance of the length of that ramp, then the amount of work that's done by that frictional force would be equal to minus F times L. And so initially there's an amount of energy equal to mgh, and finally there is an amount of energy equal to 1/2 mv squared. But finally, the energy is not going to be 1/2 mv squared. It's going to be 1/2 mv squared minus however much energy was lost due to the work done by the frictional force on that ramp. So at the bottom, the amount of energy that it would have would be, equal to that kinetic energy minus however much work was being done. And maybe you can recognize this equation as something like EI, EF, and W, right? The initial energy, the final energy, and the work done. And then maybe there is, a frictionless horizontal segment there, so it doesn't lose any more energy as it moves along the horizontal segment. But then as it starts to compress into the spring, we could write an equation that looks something like initially the kinetic energy 1/2 mv squared is going to compress the spring. And maybe at the moment of maximum compression, it's not moving anymore. The spring is totally compressed and the object momentarily comes to rest. Then the equation would be 1/2 mv squared equals 1/2 k x squared. So all of the kinetic energy that the object had went into compressing the spring some distance x. And you should think about things like this. If the object comes all the way down and compresses that spring, and then rebounds and the spring shoots it back up, there's no way that this object will ever reach that same maximum height. Not only because some of the energy was lost, but because even if all of the surfaces were frictionless, it would only go back up to the same height. And so if there's any amount of energy lost, whether it's from the friction on the plane, whether it's from the spring being compressed and then losing some energy as the spring is being compressed or jostling or moving around, then there's no way that that mass will ever reach the top of the ramp ever again.